Hello and welcome to this video. So in this video we're going to take a quick look of chapter 6 of university physics, chapter number 6 and chapter number 7. So we revise the concepts. So chapter 6 is all about work and the kinetic energy, and chapter 7 is all about work and potential energy. So first we're going to define work. So how do we define work in physics? So an object of mass m, when a force applied on a body and it covers some distance in the direction of the force, then it's in physics it's the work has been done on this object. So the work, when a force applied and object cover its distance, this is work. So work is nothing but the force times the displacement. For example, this is the position of the body, this is x1, and this is the position of the body x2. So s, which is the displacement, is nothing but x2 minus x1. So work is a dot product between the force and the displacement, and we can write this dot product fs cosine of theta, and cosine of theta is maximum when theta is 0 degree. It means when force and displacement are parallel to each other, they have the same angle, like this. They have the same angle. The distance is covering in this direction, the force applied in the same direction. Then we have the maximum work or positive work. And when cos of theta is 0, when theta is 90 degree, it means you're applying a force in this direction and object is moving in this direction, or it's not moving, or it may be silent, or maybe in the rest position. So your work is 0. So 0 work or no work. And if you are applying a force in certain direction and cos of theta is -1 when theta is 180 degree sorry. So you're applying a force in this direction and object cover in a distance in this direction. So this is the condition when the force and the displacement is anti-parallel. So you have negative work. So your work can be positive, your work can be negative, your work can be 0 as well. It depends upon. So work, we have the maximum work, like both F and S in the same direction. So we can write this is the maximum work. So the unit of work is Newton meter, because force has a unit Newton, distance or displacement has a unit meter, so it's Newton meter. And we can write Newton in terms of like F equals to MA, M is kilogram meter per second squared, so it's kilogram meter per second square into meter. So it becomes kilogram meter square per second square. So this is the unit of work, and it's equals to joules. Joule is a name of scientist. So 1 joule is 1 Newton force applied on an object, and it's cover 1 meter distance, and it is equivalent to kilogram meter squared per second square. So 1 joule. Okay, so the object is changing its position when you apply the force. So for example, in this case, so the object is, you're applying a force and it moves, like it's moved from position x1 to x2, and you are applying a net force on it. So the mass of the body is m. So at this point we can say that its speed is v1, and at this point its speed is v2. So when a force applied on a body, we learn that it produces acceleration. So in that case, our acceleration, which is along the x, is nothing but, we can define acceleration by using the equation of motion as v2 squared v1 squared divided by 2s, because it covers that s, okay, in the same direction when the force applying. So this is your acceleration, and we know that force is mass times the acceleration. So we substitute the value. Acceleration is nothing but v2 squared v1 squared divided by 2s. So here we take this s over here, multiply s by both sides, so we get fs, which is mv2 squared divided by 2 minus mv1 squared divided by 2. So we divide the 2 as well. So this is your kinetic energy 2, this is your kinetic energy 1, and this is your work done. So work done is nothing but kinetic energy at point 2 minus the kinetic energy at point 1. And this is your important result, which is the work is stored in terms of the change in kinetic energy. The work stored in change in kinetic energy. So this is your, the work done by the net force on this object is equals to the change in particles or object kinetic energy, and this is named as the work energy theorem. So this is your work energy theorem. So we can apply when the forces are when we are applying a force and it changes position, so it's actually changing its kinetic energy in time. Okay, so we can find work by drawing a work force time displacement graph. Okay, so if the object is changing its position and we are applying force and it's moving like this and then like this and like this, like this, we are applying every time a force and it's moving. So we can plot a force versus the position graph, the force versus the position graph, and we can find a force versus position graph like this. So force versus the position graph, and we can find the work by using this graph, and the work is nothing but the area under the curve. So this is your area under the curve. Okay, so if the graph is like this, applying a force and the object is at rest, so this is the area, this is the force times the position. So this is your force and this is your position, and it's just an area. And if you see, this is a rectangle, so force times the area, force times the displacement, and this area is nothing but the work. Or if you have a curve like this, you divide this curve into small interval of time, position delta x1, delta x2, delta x3. Every time you divide this into a curve, then you calculate the work like f1 delta x1 plus f2 delta x2 and so on. So then you sum all the parts, and then I fi del xi, and for summation we use integration for sum of all the things, and you can, the integration has the physical interpretation of area under the curve. So your work done is integral from position 1 to position 2 f along x dx. So this becomes your work. So we can calculate the work done by using this if we have this kind of a shape or any kind of a curve we have. So calculating the area is dividing into very small parts, and or calculating the integral. So we can have a work when the force is varying, like work with varying forces, means the force is not constant. So when the force is not constant, so how do we find the work? For example, in the case of spring is attached to that mass, and you apply a force F, and it's not constant, then you can find the work. Okay, then you can find the work. And when you have a spring, it has a spring constant, and for the force is directly proportional to the displacement. So, and this law is known as the Hooke's law. So force is directly proportional to the displacement, which upon exerting a force is happening from the mean position to the final position. Mean position is like x0 or x1 or x2, you can say anything, and this force is equals to kx, where k is f over x, and this is your spring constant. This is your spring constant, and it has a unit Newton per meter. So K has a unit Newton per meter. Okay, so when we have spring and a mass attached to the spring, then your applied force is Fkx. So we can calculate the work by x1 over x2 F applied the x. So your applied force in the case of spring is nothing but kx dx. So k is constant, you take k out of the integral, and you're left with simple integral x. And you can solve this integral using the power rule, and which says that if you have x as the power of n from x1 to x2, you will get an answer x n plus 1 over n plus 1 with your limits x1 x2, and you can apply a limit is by applying the upper limit first, x2 over n plus 1 minus the x1 n plus 1 over n plus 1. So this is how you can solve integral. This is power n. Okay, so in that case we have an integral k is x is power 1, 1 plus 1, 2 over 2, x1, x2. So you have k x2 squared over 2 minus x1 squared over 2. So we get k x2 squared over 2 minus k x1 squared over 2. So this is your work. And 1/2 kx squared minus 1/2 kx1 squared. So this is the work done by the spring. Okay. So now the concept is rate of change of work. So rate of change of work. So the rate of change of work is nothing but the power stored in it. Okay. So this is the rate of change of work, which is changing energy per unit time. So changing energy per unit time is nothing but power. So this is your average power. And when the interval is so small, it becomes an instantaneous power, means power at any instant of time. So P is nothing but limit del t tend to 0, which means the interval is so small, del V over del W over del T is nothing but dW divided by T. So this is your instantaneous power. Okay, so we have instantaneous power is dW divided by T. And what's your W? It's d by dt F dot S. Okay, and for the maximum case, we take the angle between F and S as 0. So we get d by dt Fs. So if the force is constant, so you can take this force out and this become ds over dt, where ds is displacement. So what is the rate of change of displacement? Is nothing but the velocity. So your power is nothing but the dot product of force times the velocity. So power is a scalar quantity, as your work is a scalar quantity as well. So the SI unit of power is the change in power, change in rate of change of work. Work has a unit Newton meter or joule, time has a unit second. So Newton meter over second or joule per second. Okay, and they have this name, what we call watt. And watt is the name of scientist. So the SI unit of power is watt, and watt is equals to joule per second, Newton per meter per second, or Newton meter per second. And you can write Newton meter per second is equals to kilogram meter per second squared into meter divided by second, because Newton is the unit of force and force is mass time acceleration, mass time the acceleration. So this unit become kilogram meter squared over second cube. So 1 Newton meter per second is equals to kilogram meter squared per second cube. Okay, and one thing to remember, that 1 horsepower is nothing but 746 watt. This is a conversion, horsepower. Okay, so this is your chapter 6. Now we're going to discuss the chapter 7. Okay, chapter 7 is nothing but work and potential energy. So work and potential energy. Work and the potential energy. Okay, so in the previous chapter we discussed work and kinetic energy, and the potential energy is defined as the energy of a body due to its position. Okay, so the work done by the gravitational force on the object moving from position 1 to 2 is the work done by the gravitational force, is known as the gravitational potential energy. For example, we have the object of mass m, and it's moving. For example, it's moving in the downward direction. Sorry. So I have a very bad drawing. I have a very bad drawing. So this is your y1, and after some time the object is over here from the ground. This is your y2. Okay, so your work done by the gravitational force, because when you release this object it moves downward, and the force of gravity is acting on the downward, and the object is moving its position. So the work is Fs. Okay, and now this work is stored in terms of its position. So this S is nothing but y2 minus y1. Okay, so this force is the gravity. So we have minus mg y2 minus y1, the force of the gravity, and this work, which is the gravitational potential energy, is nothing but minus mg y2 plus mg y1. So we have mg y1 minus mg y2. Okay, so the energy stored due to the position of the object with y1 is the gravitational potential energy, and we can define this gravitational potential energy as nothing but mgy. It's only along y. Okay, or mgh, which we have defined. So your work done by the gravity is nothing but minus the change in potential energy due to gravity. And what is the potential energy due to gravity? Is nothing but mgy2 minus mgy1. So the work done by the gravitational force, and this is stored in terms of its gravitational potential energy. So the work done associated with this, and the force in this case is the conservative force. So the conservative force is defined as, if we wanted to move an object from point A to B, we can either go like this or can go like this or can go like this. the force that does not depend upon the path of the object, whether you go from A to B. So the work done by this force that does not depend upon the path, does not depend upon the path followed, then this force is your conservative force, and the work done by the conservative force is nothing but the change in potential energy, which is the gravitational potential energy. In the previous chapter, we know that the work done is the stored in terms of its kinetic energy. So this is work done and this is work done. So we can equate this work done, and we have this work energy principle. So we can say that this is nothing but the K energy at 2 minus K energy at 1, and you have a work done by the conservative force is du, and means potential energy at 2 minus potential energy at 1. And how do we define the potential energy? If we equate these two equations, so we have kinetic energy 2 minus kinetic energy at 1. So we have kinetic energy 1/2 m1 squared 1/2 m1v squared equals to minus the energy, potential energy at point 2, which is mg y2 minus mg y1. So when we take this minus mg y2 mg y1, 1/2 mv2 squared 1/2 mv1 squared. So we take this 2 over here and this over here, so we get 1/2 mv2 squared plus mg y2 equals to 1/2 mv1 squared. This is plus, sorry, this is plus because minus will give you plus. So mg y1. So this is your kinetic energy and the potential energy. So you have kinetic energy and the potential energy. So this is your total energy. So total mechanical energy. So this total energy, when the forces are conserved or conservative, is total energy of the system is constant. Okay, so when only the force of gravity does work on a system, then the total mechanical energy of the system is conserved, which means that E2 equals to E1. E2 equals to E1, or E2 minus E1 equals to 0, or del E equals to 0. So it's only applicable when the gravity does work. Only the gravity does. So the total energy of the system is constant. If you have other than the gravity, so your change in energy is the work done by the other forces. It could be frictional forces, it could be any applied forces. So for the gravity, the total energy of the system is conserved. If you have any other forces that is doing work, then you have the work done by the other forces is stored in terms of its energy, change in energy. This change in energy is nothing but E2 minus E1 is the work by the other forces. and you need to identify which force is acting. For example, in the case of spring, this is applied force, okay? And if the object is moving against the friction, so the work done by the friction, so you have to consider the work done on that as well. Okay, so the total energy of the system is conserved only when the gravity does work, only the gravitational force act on this. Now if we had like added spring to the problems, then how do your potential energy work? So when you have a spring, you have a force which is equals to kx, okay? And we have learned that your work done is nothing but 1/2 kx2 minus 1/2 kx1 squared, and this energy is nothing but the elastic potential energy. So the work done is by the elastic potential energy. So your potential energy elastic will become 1/2 kx squared. This is the work done, okay? And we learned that your work done is the minus the change in potential energy, okay? So if the force is elastic, then your energy is elastic, okay? So if the elastic force is the only force doing the work, then the total energy of the system is conserved as well. So your total energy will be look like this: 1/2 mv1 squared plus 1/2 kx1 squared, 1/2 mv2 squared plus 1/2 kx2 squared. So this is your total energy of the system when you have the spring, okay? So situations when we have both the elastic and the potential energy, the gravitational potential energy, then your potential energy get the u gravitational plus u elastic. So in many problems, when you have situation when you both have the kinetic, the gravitational potential energy, or the elastic potential energy. For example, you have a spring and the object is falling on the spring, okay? So from certain height. So when this object falls, it in this problem we both have the gravitational potential energy and the elastic potential energy. And when the work done, suppose you have the gravitational force and elastic force and other force exerting on the moving object, then your total energy is nothing but the work done by the other forces, okay? Then your work done by the other forces. Total energy can be expressed in terms of the change in energy is the work done by the other forces, whether it is frictional or so the work done by the conservative force is conserved. And if we have a non-conservative forces, so when we have a non-conservative force, so non-conservative force do not store any potential energy. So non-conservative forces do not store potential energy. But they do change, but they do change the internal energy of the system. So what this non-conservative force do? So it's actually change the internal energy of the system. So it's actually change the internal energy of the system. So the law of conservation of energy means that the energy can neither be created nor be destroyed, but it can be converted into one form to another form. So your work done by the non-conservative force is equals to the change in internal energy with the minus sign. Okay, like when we push our hands up to that, we producing heat. So this change in energy is storing in terms of heat. Okay, so for a summary of chapter 6 and 7, we have the formulas for chapter 6 and 7. The first formula is work. Your work is nothing but force time displacement, or Fs cos theta. Your work is stored in terms of the change in kinetic energy. You can calculate work using the integral if you are having the graph of force times the displacement, or dx. Okay, and you have power, which is the rate of change of work. This is your average power. And then you have power, which is instantaneous, is nothing but delta t tends to 0, delta w over delta t. Okay, and which is nothing but dv dt, and your power is nothing but force time velocity. For chapter 7, you learned that your work is stored in terms of the gravitational potential energy. For the force of gravity, your energy is conserved, which means E1 equals to E2. If we have other forces, then your work is your energy will be stored in terms of the work done by the other forces. Okay, or change in energy is work done by the other forces. And if you have a non-conservative force, then your work done should be the change in internal energy. Okay, so this is the summary of chapter 6 and 7. I'll see you in the next video.